Okay, so the next set of identities we're going to be going over are the double, half, sum, and difference formulas. So if you look at your formula chart that I gave you guys, right under the Pythagorean identities, that's where they start. So we're basically going to finish up that page. Now, these identities, we don't use them as much for verifying and simplifying. These are more algebraic identities, is the way we're going to be looking at them for the most part. Okay, so the first set of identities that we're going to look at are the double angle formulas. Okay, so for sine of 2 theta, so when we have basically, say, the sine of 60, that's equal to 2 times the sine of 30 times the cosine of 30. It's kind of the way it works. It's a way of taking an angle that we know double of and reducing it to single angles. Okay. Now, we don't use these as much for, like I said, the verifying and simplifying, but more for in conjunction with the sum and difference or half angles. Okay, but they are important to know, and these are all on your formula chart. The other thing is that double angles aren't used very often because if the angle itself is on the unit circle, then double that angle is automatically on the unit circle. So basically anything in the first quadrant or anywhere on the unit circle, double it and it's still going to be on the unit circle. So we often don't use these. Now, the other one, though, it's half angle, we use a lot. So these are the half angle identities, and these are derived from the double angle. Okay? The half angles are used a lot. Okay? Like for instance, if you want to find half of, or if you want to find 15 degrees, you would do half of 30 degrees and things like that. Or if you wanted to find half of 45 degrees. Okay? As soon as you see decimals, usually you're dealing with some kind of half angle identity that we're going to be using. Okay? But these are just plug and play equations. And they're plus or minus because we have to determine which quadrant it's going to be in. So like if we're talking about sine at 15 degrees, then obviously we're going to be in the first quadrant. Okay, versus if we're talking about like the sine of 121, okay, which is going to be in the second quadrant. So depending on this plus or minus right here, will just depend on which quadrant we end up in. Okay, and notice they're all pretty consistent. Okay, sine, cosine, and tangent. So let's see how this exactly works. So the half angles, we can actually, this one we've done when we verified. I actually gave you one of these problems where we had to verify that these two were equivalent. You just didn't know that that's what we were doing. Okay, but the half angle formula itself is pretty interesting. So you can find the sine of 15 degrees using the half angle formula. Because we all know that 15 degrees is half of 30 degrees. So we can use the formula where this alpha is 30 degrees. Okay? So if we put 30 degrees right here, we put it inside as well. Just like any other function, wherever you put in x, you're going to put it into the equation. So if we want to find 15 degrees right here, 30 divided by 2 is 15 degrees. And what this allows us to do is find the 15 degree from the unit circle without actually having to use a calculator. We can use a unit circle value that we know because we should know that the cosine of 30 degrees is. And then it's just from there, just reducing. And since we're in the first quadrant, it's going to be positive. So 30 divided by 2 is 15. Cosine at 30 degrees is the square root of 3 over 2. Reduce our fraction. And then that's our answer. Okay? And this becomes our final answer right here. So this is just algebra. We're just using algebra and using the unit circle values that we know to simplify and make things easier for us. Okay? And that's how the half angle identity works. Now, the sum and the difference formulas. Okay? these are the way they work. Okay? We could have also done the sine of 15 degrees using the difference formula, because we could have said, okay, well, the sine of 15, that's like 45 minus 30, right? And we could have used the difference formula as well. But these are just formulas that we're just plugging in. So if we have sine of some a plus b, it ends up being the sine of a times cosine b plus cosine a sine b. And of course, these are on your formula chart as well, so you have them there when you need them. Okay? We don't use the tangent one very often, mainly just sine and cosine. Okay? And this is just how it works. So find the exact value of cosine of 15 degrees. Like I said, we're going to find two angles that when you add or subtract them, add up or subtract to 15 degrees. The easiest one is 45 minus 30 degrees. Then you use the formula. On your formula chart, it says cosine A times cosine B plus sine A times sine B. This is A minus B. So you just plug in angle A and angle B into the formula. Then after that, you just use their unit circle values. So cosine at 45 degrees is square root of 2 over 2. Cosine at 30 degrees is square root of 3 over 2. So these all come from the unit circle. And then you just multiply them. And remember, when you multiply, you go straight across. Do not tell me that the square root of 6 plus the square root of 2 is the square root of 8. It does not work that way. Okay? And that's the answer. Just leave it like that. That is an exact answer. Now, there are other ways of doing this one. For instance, you could have used, say, like, you could use 135 minus 120. But that would have ended up being in the second quadrant, and you'd have negatives flying around. Just depends on what you choose to do. Now, the radian one tends to be a little bit more difficult because you have to split it up into fractions. And I know you guys don't prefer fractions. But again, it ends up being basically the same thing. Okay? You're just plugging values in to the formula. Okay? All right. Now, these are the examples that I want you guys to work through. Okay, so for part A, your easiest way of figuring it out is doing sine of 45 degrees plus the sine of 30 degrees, and then you plug it into the equation. This is A plus B, and then you're just plugging in A and B into the equation, using the unit circle here, and then reducing with this as your final answer. Okay? And just leave it like that. That is an exact answer. Decimals, stay away from it if you can. Okay? Part B, you're going to split it up. Now, the easiest way of finding these is basically thinking of it, you're going to be adding two fractions of pi over 12, like that. And you're going to want to split up 7 into two fractions that are going to give us unit circle values. Now, the factors on the bottom, the factors of 12 are 1 and 12, 2 and 6, and 3 and 4. And you can see right here, 3 and 4. So basically, you're going to put like this, 4 pi over 12, which is pi over 3, and 3 pi over 12, which is pi over 4. And then simplifying, I would leave it right there, but when you actually do your radicalizing the denominator, you could also get it down to this as well. Okay? And then solution C, we're working backwards. So we have the difference of sign equation, and it's telling us this is angle A and this is angle B. So we plug those into our equation. So we get 40 minus 160, which is negative 120, which is also coterminal with 240, which gives us, our value from the unit circle, which is negative root 3 over 2. Okay. Now, here's some more examples. Okay. And this is working it backwards using radians. So basically, for this one, if you look at the equation for part A, that is your cosine equation. Since it has cosine times cosine and sine times sine, you're going to look at the cosine equation. Since it's minus, that is the sum. So basically, this is equal to cosine of pi over 3 plus pi over 6. And when you add those two together, you're going to get pi over 2, and cosine at pi over 2 is 0. And then you do the same thing for the other ones. And those are your answers. Okay? So really easy. We're just using equations. This is plug and play. Okay, so compared to the identities that we've been doing, this should be a cakewalk for you guys. Now, here's one more example. So find the exact value of sine of negative pi over 2. So again, this is about splitting it up. Okay? So since it's negative, and if you haven't really kind of figured it out yet, this 3 pi over 12 and 4 pi over 12 is shown up a couple times already. This is basically going to be, when you split it up, this is going to be 3 pi over 12 minus 4 pi over 12, which ends up being this, pi over 4 minus pi over 3. And then you just plug those into your equation for the difference equation for sine. Use your unit circle values, and you get your answer. Now, if you haven't figured this out either, almost every single one of your answers for the sum and difference equation are going to be something over 4, and it's going to be like root 2 or root 6, or sometimes 1. Okay? Because basically you're going to have a root 2 times possibly a root 3 or a 1, and you're going to get something like this every single time. Which makes sense because our unit circle values are cyclical, and they repeat. So yeah, you're going to see this. Root 2, root 3, and 1 on the numerators. So when you multiply them, you're either going to get root 2, root 3, or root 6. Okay? So make sure that you're not adding those or trying to subtract those together. Root 2 minus root 6 is not negative root 4. Don't do that, please. Okay? And that's basically all there is to it.